Okay, welcome class. Today we're going to talk about another fundamental counting principle called the Inclusion-Exclusion principle. Been trying to make this video for 5 days, so let's see how it goes. I thought I would start with an example. This is to show that this is in some ways just completely common sense. And this is the example found in Gossett, so hopefully you're somewhat familiar with decks of cards. You have a 52 card deck with starting with 2, 3, 4 all the way up to 10, and then Jack, Queen, King, Ace, and then you have 4 suits: hearts, diamonds, spades, and clubs. And the answer is, how many cards in a 52 standard in a standard 52 card deck of playing cards are face cards or hearts? Okay, and I think it's this or, which is making things kind of complicated. What we want to do is to count the number of cards out of these 52 which have either of these two properties. And the hard part is that you could have both of these properties. And that can get a little bit confusing. So okay, this as it is maybe just sort of a simple, anyone can do it if you think carefully, kind of middle school sort of counting problem. Let's just introduce some notation. Let's let F be the set of face cards. So that just means that it's a Jack, Queen, or King. And let's let H be the set of hearts. And okay, well, now we can observe some basic facts about face cards, which is that there are 3 different kinds of face cards: Jacks, Queens, and Kings, and there are 4 different suits, so that makes 12 face cards altogether. So there are, in fact, 12, the size of this set of face cards is 12, and then also there are 4 suits, so 1/4 of the deck are hearts, and so the size of the set of hearts is 13. Okay, now what are we actually trying to count? Well, what we're actually trying to count is the size of the set of cards which are either face cards or hearts. And so what we want to figure out is the set of all x such that x is either in the set of face cards or in the set of hearts. Okay, I don't know why I wrote it out like that. Maybe that's just more of a direct translation of the English sentence. But of course, when we're talking about the set of all things which are either a face card or a heart, then we're talking about the union of those two sets. So, okay, translated into mathematical language, oh my god, this is so long-winded. What we want to do is to find, to construct, maybe you can say, the set of F union H, and then to find the size of that set. That's really what we're counting. So, okay. If you don't think about this at all, you might just think, oh, well, there are 12 face cards, and there are 13 hearts. Then there must be 25 cards which are face cards or hearts. But of course that's wrong, and the reason why that's wrong is because some cards are both face cards and hearts. For example, you have the King of Hearts. Oh boy, am I really going to do this? You have the King of Hearts, the Queen of Hearts, and the Jack of Hearts. So that's 3 cards which have both of these properties, which is to say they're members of the set F and they're members of the set H. And so if you simply add 12 and 13, well, when you count all of the face cards, you're counting the King of Hearts, the Queen of Hearts, and the Jack of Hearts, and you get 12 total. But when you're counting all the hearts, you're also counting the King of Hearts, the Queen of Hearts, and the Jack of Hearts. And therefore you're double counting you're double counting these 3 cards if you were to simply add 12 and 13. Okay, so what should you do? Well, the inclusion-exclusion principle says that if you want to know the size of the union of 2 sets, and those 2 sets are not disjoint, that they have some overlap, then you simply do the obvious thing. You take the size of the set F, and you add to it the size of the set H. But now, to eliminate the fact that you have double counted elements which are in both sets, you subtract elements which are in both sets. And if an element is in set F and also in set H, then it's in the intersection of F and H. So you take the intersection of F and H, which in this case would be 3. And so here, just to talk it out one more time, we have 12 cards in the set of face cards. We have 13 hearts, but then we have 3 things which are both face cards and hearts. In other words, they're in the intersection of F and H. And so this is 25 minus 3, so this is 22. And therefore there are 22 cards in both. That have either property. Okay, this is in some sense like exactly what you would do if you had just been let alone to your own devices to think about it. And this is the kind of thing you do on, like, you know, middle school kind of intelligence tests and things like that. And maybe a picture is actually kind of nice, which makes things sort of easier. And so this is F, this is H, and what we are looking for overall is the size of F union H. And in this case, we found that there are 3 things which are both face cards and hearts. But since there were 12 face cards, it means that there's 9 here. And since there are 13 hearts in total, that means there are 10 things which are hearts and not face cards. So this picture is in some ways just summarizes this entire process. And so that's all there is to it. Okay, so the inclusion-exclusion principle is just a formalization of this way of thinking. And it is, of course, generalized. So here's something you might never have done, which is when it just gets more complicated. And it can get more and more and more complicated. So, well, this is the sort of case with 2 sets. If you have 3 sets, of course, maybe the picture is appropriate here, then you have, here's A, here's B, and here's C. And now, suppose, this is what the inclusion-exclusion principle is good for, suppose what you want is to find the size of A union B union C. So we'd like to find the total number of objects that are in all of the sets. Well, this can be calculated by, this is what the inclusion-exclusion principle says in the case of 3 sets. You should take the total number of objects which are in set A, or elements in set A, and then add to it the total number of elements in set B, and add to that the total number of elements in set C. Well, okay, if you do that, you have overcounted. This is the correct answer only if these sets are all disjoint, so they have no elements in common. But according to the most general case, which is what this picture illustrates, there might be considerable overlap. And so we have overcounted, and it's actually subtle by how much we've overcounted. It depends. If there is an object, for example, sitting right here in the intersection of A and B, but not in C, then it's been counted twice. If there's an object which is just in A, it's been counted once, so correctly. If there is an object which is in A and B and C, it's been counted 3 times, according to this sort of erroneous initial analysis. Okay, so how are we going to handle this? Well, we should, let's first deal with the overlaps between any 2 sets. So now, just like before, I'm going to subtract things which are in the intersection of A and B, because if something is in A and B, the idea is where that star is, then we just counted it twice. So now if we count it twice and subtract it once, then we're counting it correctly. And we should also subtract out the things which are in A and C, but not B. So that kind of object is the idea. And then also subtract out the things which are in B and C. And this is getting closer to the right answer, but this is still not totally correct. And that's because if there is an object which is in fact in all 3 of those sets, well, now we have not properly counted that object, because when we included it when we counted it here, we counted it once when we counted it as an element of A, twice when we counted it as an element of B, and again when we counted it as an element of C. So we counted it 3 times, but then since that object or element is in A and B, we subtracted it. But we also subtracted it as being a member of A and C, and we also subtracted it as being a member of B and C. And so we've sort of triple counted it, but then triple uncounted it, or we've triple corrected is maybe a word I could use. We've triple corrected by uncounting it 3 times, and so it still remains undercounted. And so now finally we add all the objects which suffered from that counting error are the objects which are in the intersection of all 3 sets. And so we add in A intersect B intersect C. Okay, and now you can just convince yourself that that this is now the correct analysis because and again, most people don't even think to sort of prove this because it's just so clear. But what you should do, I suppose, is consider objects which are in any one of these spots on the Venn diagram, so to speak, and see whether they've been properly counted. So, okay, just let's do it. Take an object which is just here, for example, in A but not in B and not in C. Well, that object on the left-hand side, this is sort of a if you want to be very careful about this, I suppose that this statement here, this equality, is kind of a theorem, and this theorem is saying that these 2 sets have kind of the same size. And to prove that these 2 sets have the same size, then I'm performing a kind of a counting argument. So it is a combinatorial argument in a kind of a way, which is saying that both of these methods count every are counting the same thing in 2 different ways, and therefore they must be equal. And so why are we counting the same thing in 2 different ways? Well, because this method of counting on the left, which is to simply throw all the elements together into one big set and then see how big that set is will count the objects correctly. But if you take an object, then the right-hand side will also count those objects correctly. So okay, let's just push on here. So if you take an object here, well, if there's an object which is in A, then of course it appears once in A union B union C, and so it gets counted once. Now we just have to ensure that on the right-hand side it also gets counted once. And it just does, because it's in A, so it gets counted once, but it's not in B, and it's not in C, so these are all 0. Is it in A intersect B? No, it's not. And it's not here, and it's not here, and it's not here, and it's not here. So all of these are 0. That's kind of the boring one. And then if you take an object here, which is in A and B, then it gets counted once in A, it gets counted twice in B, but then it gets subtracted once when you subtract A intersect B, and it doesn't get counted here because, okay, I think we're good. Oh, and then the last one is we have already talked this out. If it's in the middle of all 3, then it gets counted once, twice, 3 times, it gets subtracted 3 times, and then it gets counted once, and so it's all correct. Okay, good. Let's do an example of why it's actually useful to have the inclusion-exclusion principle in your sort of bank of knowledge, versus this just being an intuitive concept that you don't need school to teach you about. And I guess the answer is, like anything, when the examples get hard, it's nice to have a sort of a theoretical model to fall back on of how to think about these problems. Okay, I'm going to do, because if we were live in class, I would come up with a cute example using my students and their various properties, like junior, senior, blonde hair, plays sports, who knows. But being by myself, I will just use an example from Gossip. And I don't know whether to be happy or sad that Gossip has picked extremely difficult examples. In some ways, you have to pick extremely difficult examples to be convinced that that using the inclusion-exclusion principle is worth your time versus just being really smart and making a picture and just kind of figuring it out, which is probably how you would do any problem that was relatively easy. Okay, so let's do this in a kind of a formal, methodical way. This is one of the homework problems. So this is number 15 on page 245 of Discrete Math with Proof by Eric Gossett. Woo! Here we go. This is what it says. I'll read it aloud. A company wanted to hire some newly graduated college students. They decided to send one of their employees from the personnel department to a job fair. Okay, so someone is coming to a job fair at a college. That employee's role was to screen the applicants. Students who passed the screen were invited for interviews. Okay, so this person doesn't have a lot of power, but they're gonna they're gonna interview, you know, possibly hundreds of people in a very, very brief kind of way. Not even interviewing, just screening, just checking to make sure that they meet the minimum standards, and then real interviews are gonna happen later. Okay, so I find this to be somewhat depressing series of things to screen for, but here are the 3 questions that Gossett thinks that a job screener from an HR department. Maybe this is like a dig at HR departments in a kind of a subtle way. But all right, basically, are their resumes free of grammatical and spelling errors? So is their resume okay, or is their resume egregiously full of mistakes, making this person seem like they don't have an attention to detail? Are they wearing appropriate clothing, whatever that may be, cool t-shirts or whatever it is? And are they willing to work for a salary in the range specified by the company? So are their demands for money too high so that they just shouldn't be considered for this job because we can't pay them enough? Okay, and so let's now consider, well, let's just keep reading. The employee had contact with 65 students at the job fair. Only 30 of them had mechanically acceptable resumes. There were 44 students who were willing to consider a job at the salary range offered. Clothing was a problem. 37 students did not meet the company's dress standards, so they were not wearing cool enough t-shirts. Some of the students met 2 of the 3 standards. 18 met the resume and dress requirements, 15 met the resume and salary standards, 16 met the dress and salary requirements. On the other hand, 5 students failed all 3 screens. How many students were offered interviews, and how many students passed the resume screen but failed the other 2? Okay, if you gave me a long time, I could probably do this by just screwing around and drawing pictures and being smart and stuff like that. But I might very well screw it up. And this is the kind of, I don't know, like, question they give to see if you can, I don't know. Okay, let's start. Alright, translating some facts into mathematical language. The employee had contact with the 65 students at the job fair. Okay, so there were 65 total students at the job fair. And that means that there is sort of a kind of a universe, so to speak, of size 65. 65 is the number, the total, I'm going to call this the universe. It's the total number of students that were contacted by the HR department at all. Okay, and then only 30 of them had mechanically acceptable resumes. Okay, well, let's introduce some notation. So let's let R be, just like we did before, the size of the, I guess just let R be the set of students with good resumes. So with good resumes. So that is resumes free from grammatical errors and stuff like that. Okay? Let's let C be the set of students with acceptable clothing. And let what's the last one? Oh, S be the set of students whose or with salary with appropriate salary requirements. I'll just say. So the amount of money they were looking for was equal to the amount of money that's being offered. Okay. Well, then we can translate this entire problem into mathematical language. Let's go. Only 30 of them had mechanically acceptable resumes. Okay, well then that just means that, so this is fact 1, is that the size of the set of people whose resumes were appropriate was 30. Oh, and if we're building this, well, maybe we'll just hold off on that. Next sentence. There were 44 students who were willing to consider a job at the salary range offered. In other words, the size of the set of people with appropriate salary requirements was 44. So that's like fact number 2. Next, clothing was a problem. 37 students did not meet the company's dress standards. Okay, so let's just call that C complement. C complement is the number of people who did not have appropriate clothing. So t-shirts not cool enough. And this was given to me directly by the problem as 37. But of course, if 37 people did not have appropriate clothing requirements, and there were 65 total people, then that means that 28 of them did have appropriate salary requirements. So that means that that's 28. Okay, next. Okay, some of the students met 2 of the 3 standards. 18 met the resume and dress requirements. Okay, so in other words, that means that some of them met 18 met the resume and dress requirements. Have I just done this wrong? Oh, I just wrote a bunch of nonsense on my paper. Wow. Okay, good. So, good. Using my brain then, if 18 met the resume and dress requirements, that means that these students had a good resume and good clothes. Resume and dress requirements and clothing. So that means that they were in the intersection of R and C. They both met they both had good resumes and had good clothing. Some of the 18 met the resume and dress requirements. Yeah. So this is 18. Good. Next, 15 met the resume and salary standards. So that means they had a good resume and they were looking for a salary in the appropriate range. There are 15 people with that that met that condition. 16 met the dress and salary requirements. So cha-cha-cha is 16. Dress requirements and salary requirements. And finally, 5 students failed all 3 screens. 5 students failed all 3 screens. So that means, I guess, what's the best way to put that? There were 5 students who didn't have good resumes, didn't have acceptable clothing, and didn't. Okay, so if there were 65 total students, then that means that, and 5 of them failed all 3 screens, then if 65 students were contacted, 5 of them met none of the requirements at all, then it means that 60 of them met at least one of the requirements. So perhaps the best way to translate this from the problem is that if you take R union C union S, what should that mean? That's anyone who had a good resume or had good clothing or had a good salary, all together. So just met any one of those 3 requirements or greater, and you take the complement of that, then these are all the people who didn't meet any of those requirements. And if you didn't meet any of those requirements, well, there were 5 of you. Which is to say, Gossip's making us work for it a little bit, which is to say that, let's see if I have space here, that the size of our union C, union S, is in fact 60. So 60 of the 65 met at least one requirement. All right, and finally, this is so slow. Finally, the question is, how many students were offered interviews? Okay, well, you only offer an interview to someone who meets all 3 requirements. So that means we want to know how many people were had good resume and good clothing and good salary. Okay, so that was the hard part, I think, just the reading and the thinking and the coming up with variables and the modeling. What I have now done is I've reduced this entire problem into a math problem. I have like 7 or 8 pieces of information. I have these 3 sets, R, S, and C. I know the size of R. I know the size of S. I know the size of C. I know the size of R intersect C, R intersect S, and C intersect S. And I also know the size of R union C union S, and I want the size of R intersect C, R intersect S. Now, and so what can we do? We can apply the inclusion-exclusion principle. So apply the inclusion-exclusion principle and exclusion. And what does it have to say about the relationship between the size of 3 sets? Well, it says, quite simply, that if you want to know the size of R union C union S, then, just as we did a few minutes ago, you should take the size of R plus the size of C plus the size of S, subtract from it the size of R intersect C, accounting for the double counting for objects which are in R and C, subtracting out R intersect S, the double counting of R and S, and you subtract out C intersect S, the double counting of people who are in set C and also set S. But then you have overcorrected, because if someone was in all 3 sets, you have counted them 3 times and subtracted them 3 times, and so we need to add those back in. So R intersect C intersect S. Okay, this is just a straightforward statement of the inclusion-exclusion principle. I see that I did not leave like space, so too bad. Now I just look over here. What do I have? I got 30. This is 28. This is 44. This is 18. This is 15. This 16. This I don't know. No, this is 60, and this is what I don't know. So calling this like X or something for a second, what that means is that 60 is 30 plus 28 plus 44 minus 18 minus 15 minus 16 plus X. And now we just like do it. So however, we're gonna do this 42 is 11, 9? Is it 9? I got 9, 7 apparently is the answer. Let me just do my arithmetic again. I'll just do this the lame way. 60, 72, 102 minus, and then that's something, 11, 19, and 30 minus 49 plus X. 51, 53, yeah. So 60 is 53. So X is 7. Okay, and then the answer is, therefore, that there must have been 7 people who were in all 3, that met all 3 requirements, and those 7 people were offered interviews. Okay, how else would you do this problem? Not like this is another way to do this problem. Another way to do this problem is where you just kind of hack it out by just drawing a bunch of circles and trying to be really careful. So I can't stop you from doing it this way, and it might actually be faster, but if you want to kind of keep track of the logic of what you're doing in a sort of slow, methodical manner in which it's clear to anyone watching what sorts of logic and computations you're actually doing, then I think this is the way to do it. If you just want to get the answer really, really fast because it's like a math team problem or something like this, then I would probably just go to the picture and then just try not to screw up. R, S, and the picture, I'm not saying the picture is bad, I'm saying the picture might be even better. What's the picture way of doing this? It doesn't require doing a lot of things like in your head though, so to speak. So what do I know? R is 30, so I just kind of fill in the things that I know. Well, the problem is, this problem is sort of forcing you to not do it with the picture because they're not giving it to you in the easy kind of way. They're giving it to you in a way that's kind of hard, right? So what I don't know is what's in here. So it's like, that's X. But I know like R intersect S is 15, so then that means that this must be like 15 minus X, I suppose. Okay. R intersects C is 18, so this would be 18 minus X. And then S intersects C. I think this is probably how they have you do it in math team. I don't actually know. That would be 16 minus X. And then because, for example, R is 30, then all that stuff is 33 minus X. So if that's all 33 minus X, then this has to be X minus 3. Did I even do that right? That has to be X 33 minus X plus X minus 3 would be 30. Yeah. And then is this going to somehow lead to an answer at some point? Oh, and then somehow I know that all of them is, this is actually not the way, this is not the smart way to do this. The smart way to do this, I guess, I didn't really prepare for this, to think through this carefully, but if I was just put on the spot to do this as fast as possible, not on a video, what would I do? I guess I would, I don't know, I would just kind of crank it out somehow. Maybe this is an argument for just doing it this kind of formal way. Well, anyway, let's just fill in the numbers now. Now that I know that this is 7, and I know that R intersects S is 15, then it makes that 8, and it makes R intersects C is 15, so it makes that 8 as well. This is what my picture is telling me, except it isn't. What the hell have I done wrong? 7, I just made a mistake. That would be 11, because R intersects C is 18, and so that would be 11. C intersect S is 16, so that would make that 9. And now, what can I say about R? Well, 15